There are now over 5,000 exoplanets discovered, including many that could be cousins of the Earth. As amazing as that is, many of us want more. We want to actually visit these places someday, or at least send a robot that could perhaps send back photos. So today, let's do something a little bit different and use a tier list to rank the different interstellar propulsion technologies that have been proposed. The actual rankings will of course be my own opinion, but I will briefly outline each idea as we go so you can form your own judgment and leave this video as your local neighborhood expert in interstellar propulsion. There are two basic criteria that I'm going to use to judge these. First, how fast does it go? Pretty obvious, faster ships are better because, let's face it, we're all just too impatient. Second, how technologically feasible is it? Again, I don't want to wait 1,000 years for us to invent the technology. I want it in my lifetime. There will be bonus points for ideas that can transport humans and not just robots. And that generally means it needs to work with very heavy ships packed with life support systems, as well as requiring the ship to actually be safe for our frail human bodies. And I will consider low-cost technologies for additional bonus points because, hey, someone's going to have to pay for this. There's actually a very long list of possible interstellar propulsion ideas out there, but many of them are just variants and tweaks of each other. So the list that we're going to be working with today is definitely not exhaustive, but it covers most of the bases. So let's kick things off with the one interstellar propulsion technology that has actually been proven to work so far, and that's chemical rockets. All rockets, like this beautiful Starship model I have here, work by expelling propellant out of the back, a bit like this. Now, propellant carries momentum, and so by the law of the conservation of momentum, the ship will have to move in the opposite direction. The change in velocity, or delta V, that one gets out of such systems is governed by the Tsiolkovsky-Rockett equation, and that tells us that we want high-speed propellant. To get the propellant to move at all, you need an energy source, and for chemical rockets, that energy source is chemical reactions. Most commonly, it's hydrogen and oxygen which combine together to make water. Now, the problem with all rockets is that you have to bring your propellant with you, and that stuff is heavy. For example, for the Saturn V that launched Neil Armstrong, 94% of the ship's mass was just fuel. However, chemical rockets have excellent thrust-to-weight ratios, almost immediate on-off switches, and we can control the rate of reactions very easily. That gives us fine throttle control. But the actual impulse they impart just isn't that high, yielding speeds of 10 to 15 kilometers per second, which by itself just isn't fast enough to escape the sun's gravity and go interstellar. However, we can always steal some extra speed from the planets using gravitational slingshots. In fact, we've already done this 5 times for Voyagers 1 and 2, Pioneers 10 and 11, and the New Horizons spacecraft. They are all interstellar. The fastest of these, Voyager 1, is escaping the solar system at about 17 kilometers per second, meaning that it travels 1 light year every 18,000 years. So I'm going to rank this as B tier because it actually does work, it's proven to do so, and to boot, it can actually move humans around as well, but it's obviously slower than we'd like and not particularly cheap. Next, let's stick with rockets but move to the nuclear thermal rocket, or NTR. Okay, so rockets work by expelling propellant. The faster, the better, by the Rockett equation. If the propellant is a gas, then Maxwellian physics tells us that the velocity of the particles is proportional to the square root of the gas temperature divided by the molecular mass. So that means that we want hot gas and light particles to maximize speed. In a chemical rocket system, we supply the heat to warm up the gas using combustion. But what if instead we use a nuclear fission reactor? Stick some uranium in a reaction chamber, bombard it with neutrons to control a fission reaction, and then use the heat generated to warm up a propellant gas. Since light gases are best, let's use hydrogen. That's the basic idea behind NTR. Now, we've never flown such a rocket, but we did test and actually build some designs back in the 1950s and 60s. The advantage is that the energy density of the nuclear strong force is far greater than that of chemical electromagnetic bonds. But the real question is, how do you tap that in a controlled way? For rockets, all we really care about are maximum thrust and specific impulse, where the latter really tracks how efficient the engine is. Now, unfortunately, NTR produces inferior thrust to our best chemical rockets. It's about the same as an upper stage component. So unfortunately, the thrust is insufficient to escape the Earth's gravity, and so you'd have to use some kind of chemical rocket system to get it up there in the first place. But what it lacks in thrust, it makes up for in efficiency, delivering about twice the impulse of the space shuttle, approaching 1,000 seconds. So twice the efficiency means half the propellant needed. NASA is rediscovering this 1950s technology with a planned demonstrator called Draco, so look out for that. Alright, so let's rank it. On the downside, we are launching high-grade nuclear fission material into space, which is obviously risky. Further, nuclear energy densities are about 1,000,000 times greater than that of chemical energy systems, and yet here, we're only getting like a 2x improvement, so it seems like we're leaving a lot of wasted potential on the table here. But it's technologically feasible, there is a planned demo mission, and it has twice the specific impulse of chemical systems, so I'm going to put this as A tier. But if you want more nuclear bang for your buck, then good news, Nuclear Pulse is here for you. Okay, this is going to sound a little wild. The plan is to detonate a series of nuclear bombs behind the ship, whose explosions then smash into a so-called pusher plate attached to the vessel. To absorb the impact, the pusher plate is obviously very thick and durable and is sometimes allowed to wind along a spring or a tether. Such a design would produce an order of magnitude greater specific impulse than the NTR and has been extensively studied in the 1950s and 60s as part of Project Orion, a concept study supported by DARPA which could reach Mars in 4 weeks. Testing this idea is currently prohibited under the Partial Test Ban Treaty, and obviously using it in the Earth's atmosphere would be incredibly dangerous. Another variant design called Project Medusa is claimed to be capable of a specific impulse of up to 100,000 seconds, using a giant parachute to catch the explosions and then drag along the ship. There's many variants like this, for example using H-bombs to increase the yield further. But for smoother accelerations, we need a series of small bombs, but plutonium's critical mass of about 10 kilograms seemingly sets a minimum scale, and so some have suggested seeding the bombs with a hint of antimatter that can kickstart the chain reaction and let you get away with far smaller pellets. In the Project Daedalus concept study, small pellets of helium-3, which would be harvested from Jupiter's atmosphere, are then fused using laser inertial confinement. A NASA-sponsored follow-up project called Project Longshot refined these ideas and claimed that it could reach Alpha Centauri in a century. As you can see, it's hard to pin down exactly what a nuclear pulse system would look like or be capable of, and the feasibility varies from 1950s level of technology to something which is at least many decades away. So I'm tempted to put this down in the B tier category for feasibility concerns, but given the number of extensive studies on this idea, let's make it A tier. You know, an interesting issue with the nuclear pulse idea is that if an alien civilization was using it, then that seems like something we should be able to detect from far away, spraying neutrinos and light in all directions. I think that could be a really interesting study for astronomy. How far away could we detect one of these things using existing telescopes? Now, we might be interested in spying on our neighbors, but you probably don't want to be tracked. And that's where the sponsor of today's video comes in. That's Incogni.com. So the sad truth is that there are companies out there who are dedicated to just harvesting and aggregating your personal data without your consent. I'm talking home addresses, phone numbers, employment history, and even social security numbers. Incogni is a subscription service that I've been using that fights back for you. They scan databases for your personal data, and then they email those companies and persistently request that information be deleted until they comply with the law. Log into their website and you can see just how many databases are harvesting your data and the status of their compliance requests. My phone used to ring off the hook with spam calls to such a degree that I basically gave up answering the phone anymore. In another case, somebody called me up and actually read out my home address to me using information they dug up online. I reached a point where I was just sick of this crap. If you want to fight back against this too, then here's what you do. Head to incogni.com/coolworlds and make sure you use the code coolworlds to get an exclusive, get this, 60% off their annual plan. Once again, that's incogni.com/coolworlds, code coolworlds. Now back to the video. So far, we have been focused on rockets, but now let's mix it up and talk about sails. The simplest idea here is the solar sail, which means it's powered by the sun and the sun alone. Sails are radically different from rockets in that there's no fuel aboard, meaning that they are decoupled from the so-called tyranny of the rocket equation. It's strange to think about, but light carries momentum even though it has no mass. That's because it has a finite amount of energy, and Einstein teaches us that momentum can be expressed as energy divided by the speed of light. For a visible light photon, the momentum carried is unimaginably small, some 10 to the 27 times smaller than a baseball being tossed. However, at Earth's distance from the sun, every square meter receives several times 10 to the 21 photons each and every second. Light thus exerts a force known as radiation pressure upon everything it strikes, but it's a whisper of a force. In most cases, the sun's inward gravitational pull is far greater than that of the outward radiation pressure. But gravity only cares about mass, and radiation pressure only cares about surface area. So, if we made something extremely thin and light, radiation pressure could win out, and that is the idea behind a sail. To go interstellar, the outward radiation force has to exceed the inward gravitational pull. Do this at any distance from the sun and you're good to go, because both forces conveniently drop off as the square of distance. However, this requirement ends up meaning that you need something which is 0.8 grams per meter squared, which is extremely difficult to manufacture. For example, if the sail were made of aluminium, one of our lightest metals, that translates to a piece of aluminium that's about 1,000 atoms thick, or 200 times thinner than a human hair. On the plus side, we have successfully tested some solar sails such as Icarus, Light Sail 2, and Nano Sail, but all of these were 2 orders of magnitude too heavy to go interstellar. So, plus points for some testing already, but it's still a long way off what we need. For me, this is either B or C tier. It's close, but I think I'll go C tier because it's slow and it can never really get humans out of the solar system. Now, a variant of the solar sail is the fission sail proposed by Robert Forward. This laces the sail with radioactive fissile material. The decay products pop off in random directions and they carry away momentum as they do. If the sunlit side of the sail is radioactive, then the forward traveling decay products just bump into the front of the sail and don't change the overall momentum. But if they fly out of the back, then that's propellant and it acts like a little rocket. The beauty here is that you just need to add a very thin layer of radioactive material into your sail and it could provide a little bit of thrust for potentially centuries depending on what material you use. So the fission sail is really a hack, a mod of the standard sail design. Given the solar sail was a borderline B/C tier, I'm going to bump this up to B tier. The fastest version of a light sail is the laser sail, although really any form of directed energy will work, not just lasers. The sun dumps about a kilowatt of power onto every square meter of the Earth's day side, which sounds like a lot, but really isn't enough to give these sails enough momentum. So instead, let's replace the sun with a series of laser beams to get things moving faster. Silicon Valley billionaire Yuri Milner seed-funded a $100 million project to reach Alpha Centauri in his lifetime, and he gathered a group of brilliant physicists to figure out how, and light sails was the answer that they converged upon. Named Breakthrough Starshot, this project proposes to use an array of 100 gigawatt lasers, yes, gigawatt, aimed at a curved sail a few meters across and weighing just a few grams, and that will accelerate it to about 20% the speed of light. There are many engineering challenges here. For example, the sail has to be incredibly reflective to avoid burning up in that 100 gigawatt laser beam. Balancing in the beam for several minutes of acceleration is also a major challenge, requiring a ball-shaped sail. But I've been impressed with the clever solutions emerging from the team, such as embedding the electronics in the sail itself and using the sail as an antenna for communications. Another advantage is that potentially thousands of these things could be built at scale. Really, the main cost driver is the initial laser system and just building and testing the first designs. So look, if we want a photo of an exoplanet in our lifetimes, for me, this is our best shot right now, and so I am going to put this as S tier. Okay, I need to speed up, but the next few should be pretty fast. Next up, we have the Alcubierre Drive, or simply warp drive. This actually really isn't a drive, it's more of a metric in general relativity to bend spacetime in such a way that a ship would seem to move at potentially superluminal speeds. I've talked about this idea extensively in a previous video, so just go check that one out, but it has many problems. For me, the biggest of which is that this is a time machine and thus it violates causality. As much as I wish this one was legit, I have to put it D tier based on what we know right now. Let's look at wormholes, similar kind of ideas, holes through space such that the ship doesn't really have to travel fast at all, we just jump through a portal to some distant destination. Unfortunately, we have no evidence for naturally occurring wormholes, and again, their existence would lead to causality violations in the universe. Stephen Hawking suggested that any faster-than-light system like this is always prohibited to protect the timeline. For example, with two wormholes, they would actually create a feedback effect, like a microphone being moved close to a speaker, building up infinite energy between them that instantaneously destabilizes the openings. I might do a video about this one day, but for now, I'm okay putting this down here alongside the Alcubierre Drive. Next up, we have antimatter, the ultimate in energy density, allowing us to maximally exploit Einstein's E = mc². Pound for pound, antimatter has an energy density about 4 billion times greater than that of the best chemical fuels. It really doesn't get any better than this. But unlike chemical fuel, we have no deposits of antimatter that we can mine. We have to make this stuff ourselves. Particle accelerators like the Large Hadron Collider produce about 10 nanograms per year, but we essentially just immediately annihilate that. It is estimated that if we wanted to manufacture even a milligram of the stuff, it would cost us about $100 trillion. This is just a non-starter from a practical perspective. And that's a real shame because the reactions largely release photons which have an exhaust velocity equal to the speed of light. Thus, by the Rockett equation, such a system would be easily capable of true relativistic flight. Look, if we had a giant mine of this stuff somewhere on Earth, then we would be heading to Alpha Centauri by now already. But of course, such a mine would be incredibly dangerous and really shouldn't exist in the first place. So ranking this, look, antimatter is at least a proven real thing, so it's not D tier. I'll put it as C tier. All right, let's just speed around a few more for fun. Mind upload, as in uploading your brain to a machine and then beaming that information to a computer on a distant exoplanet. Obvious problem is that you have to have a computer at that distant location already before you obviously do this. But even putting that aside, personally, I'm a little bit skeptical that we'll ever be able to do a true mind upload of the human brain, but I do think we could one day send an artificial general intelligence across space this way. This is obviously a long way off, but again, it doesn't violate physics, and so we'll go C tier here. Next up, we have negative mass. This is a fun one. Consider that a pair of positive mass particles gravitationally attract one another and thus move together. If negatives existed, then a pair of them would repel since the acceleration vectors now flip over. So, if we had a positive and a negative, we would have the bizarre situation where the two would actually chase each other, accelerating forever in a straight line. This would obviously be very useful for interstellar propulsion, but I have to put it D tier because negative masses is a completely made-up concept. There's no reason to think they exist. Now it's time for a personal favorite, the Halo Drive. Well, look, I'm obviously a little bit biased here because I invented the damn thing, and you can learn all about the Halo Drive in our previous video on this topic. This is kind of like a gravitational slingshot on steroids. We approach a black hole, fire a laser beam around it, which skirts the event horizon. Due to either binary motion or frame dragging of the black holes, or in fact even both, the laser beam will skirt around the black holes, steal momentum from it, and then come back to the ship and push it away at high speed. This can reach up to 4/3 the speed of the black hole, which is often relativistic. The downside here is that you need a black hole. The nearest natural one is likely a few dozen light years away, but perhaps there is a primordial one much closer than that. But on the plus side, it requires no new technology. It can accelerate truly gigantic vessels, even planet-sized things, and finally, it is energetically free. But I have to admit, this is more of the highway system than the on-ramp. I think it's pretty cool, so we're going B tier. All right, time for two last techniques. The ion drive really deserves more time, but it is essentially a rocket where the propellant are ions, that is, charged particles, spewed out of the back using electromagnetic fields. So you do need a separate power system to generate those fields, but that power system can be whatever you want. Further, the fields are accelerating particles without using heat, so there are no limitations of melting your ship if you go too hot here. Because the propellant can move so fast, ion drives are very efficient, specific impulses of several thousand, and they've been used in space, such as Deep Space One and the Dawn spacecraft. However, they produce tiny thrusts, meaning they take a long time to accelerate to useful speeds, so overall, I'm going to put this as B tier. Finally, we have the Bussard Ramjet, which aims to just smash into hydrogen atoms floating around in space, harvest them as a fuel, and then use that for nuclear fusion. Devised by Robert Bussard, the idea has been criticized as being unfeasible due to the challenges of compressing the gas without losing excessive energy. There's also the challenges of interactions with the solar wind and also just the challenges of the extreme technologies needed here. It doesn't violate physics, but it is extremely advanced, so I'm going to put this down here as C tier. Okay, that's my list, but I'm sure you have your own opinions. Please do let me know down below in the comments. As I said, this wasn't exhaustive, but I think it gives us a good smorgasbord of the possibilities and how they compare. You know, interstellar travel has always fascinated me. It feels like our destiny to reach for the stars and one day discover all of those distant cosmic horizons. I've accepted that I will never step foot on an exoplanet, as much as I wish that was not the case. But a photo in my lifetime, I think that is possible. And perhaps we could see some kind of slow but still interstellar ships departing in our lifetimes too. Missions designed to last for centuries as gifts to our descendants. The main thing that I take away by thinking about this problem is that we really limit ourselves if we insist on only thinking about ideas which are executable in human lifetimes. If we refuse to bother unless the journey could be completed in a few decades or less, then the day may never come when we'll reach an exoplanet. But if we relax that, and we are willing to entertain missions that could last for centuries, look, we could plausibly do it now. We could launch ships that our great-great-grandchildren reap the benefit from. Yes, you won't see the fruit from that, nor indeed myself, but humanity will. Some projects, like building a cathedral, just take centuries to complete, and that's okay, because it's not always all about the individual. Sometimes it's about the society. So, until next time, stay thoughtful and stay curious. Hey, thank you so much for watching this video, everybody. I hope you enjoyed it. Be sure to hit the like and subscribe buttons. If you want to become a supporter to my research team, the Coolwords Lab, you can use the link up above, down below. I sincerely appreciate it. And if you haven't already seen it, we have a podcast. Just go to Coolwords Podcast on YouTube. Again, links down below and check that out too. Thanks again for watching.